or any processor which is asynchronous? None.
No.
They are all synchronized. They have to operate at some clock frequency. And where and how this clock will be distributed in a chip? That would be, traversing to the longest distance, all corners of the chip. This is just one side. On the top, if you see, you have different modules, right? And all of those modules will be connected with each other. If I show you, this is what your chip top layer would be, and you have different modules. Now, what are these modules? Some might be memory, some might be ADC, some might be single conditioning, analog circuits, digital circuits. There is a complete design team that looks only on distribution of clock. H tree, Y tree, this tree, that tree, every tree they do with the interconnects, right? So now these interconnects, once they have the resistive parasitic associated with them, what will happen?
Isolated.
You'll have a lot of delay, power dissipation. Everything goes with resistance, right? And very interested by him, the resistive parasitics will grow so much that probably your delay and other things, your skew, I won't be able to discuss all these things in detail. Skew, jitters, right? Everything will come into picture. And these clock signals are very sensitive as the frequency goes up. Your frequency components becomes higher and higher within your rise time and fall time of that signal. Right? Are you getting my point? All of you are with me? Yes. Yeah, even if you gain 20 to 30% out of this lecture, it's fine. No problem. But the important thing is that we should understand what is being talked about, what are the challenges, right? When this industry is making it. So copper itself of what actually industry is going to work on. So we are going to talk something about spintronics later on. It's not only theoretical, it has been already realized. The companies are there now, and all your mobile phones and laptops are using these kind of memories also. So we'll be talking about all those things. Anyway, I'm just laying the foundation, the challenges which industry has to go through. We do talk about a lot of things, and interconnect designers also talk about, especially about optical interconnects, and then about CMPs, graphene, TMDs, and all these kind of interconnects. So we also started doing a lot of analysis, leaving aside copper, and started talking about graphene, multi-layer graphene, carbon nanotubes, mixed carbon nanotubes, double carbon nanotube, single carbon nanotube, multi-layer carbon nanotube, all kind of carbon nanotubes and graphenes. Right? Reason being that we were driven by the fact that what industry is going to do next, and how could we help them out. The challenges which were there with the copper could be addressed by these kind of materials, but industry is really reluctant. For them, everything is money, and of course it. The chip industry is so costly to afford, so they won't be changing suddenly, copper to graphene. Oh, Professor Kaushik said that graphene is going to work well. Okay, stop doing with copper and start doing with graphene. They won't do this way. They will do a lot of economics after that. Right? How much I'm going to spend on changing the fabrication line. Entire Europe, has been vouching a lot for graphene. They have big projects, big missions for graphene, but still industry will not change it. They are really reluctant. They are still going with CMOS and copper, right? And then we do talk a lot about optical. There are some cases where researchers have already shown, and some of the optical interconnects have also been used. But optical interconnects itself has a lot of challenges that needs to be addressed. Now, when you talk about optical interconnects, they have to be driven by some source. And what is that source? Laser source. That laser has to be built within the chip. and then you need to have optical detectors that will be detecting all those optical signals. Right? So every time whenever you work out with these optical interconnects, you need to have a laser diode, and then you have to make out all those waveguides, and finally it has to be detected, and then converted again into electrical signal. So then conversions, different conversions from optical to electrical, electrical to optical, and so many conversions have to be done. And sometimes these overheads of this laser source and detection is so much that probably it becomes really unfair to use these kind of optical interconnects. Right? And therefore industry is still going on with copper. They are facing a lot of challenges, but changeover is really difficult unless the technology is established very well. Is there anyone who is working on optical domain? Okay, if you go to the nitty-gritties of optical domains, you'll find out that all these optical sources have to be very well aligned with the waveguide, and also when you're decoupling or coupling them with different other detectors, you have to make sure that they are coupled very well, aligned very well. So even a change of 1 degree of angle can actually ruin the overall benefits. Although optical has a lot of benefits, no doubt about it. It has come up to PCBs. The PCBs, we are using optical sources, optical and all those things. But within the chip, somewhat challenging. People have showcased it, but still challenge. So we started out, we worked on copper interconnects, optical, all these kind of CNTs, graphene, TNTs, all these kind of materials we have used and seen their benefits. So apart from this, we also talk about interconnects when we have to go with 3D ICs. As of now, what we are seeing is silicon on the one layer, but we can have 3D ICs where we can build up number of silicon layers, right? And all of these silicon layers have to be connected with each other, right? And that would be done using TSVs through silicon vias. They have to go through the silicon, so they have their own challenges. You have MOSFET effects even with these TSVs because you have metal in the through silicon via, semiconductor, right? Oxide, so you have MOS effect. But anyway, we won't go into the nitty-gritties. It's itself a big area of research. No worries. Maybe if someone plans to do it, it's a very good area to talk about. So 3D ICs, right? Why are we motivated by 3D ICs? 3D ICs are there. Industries have started on those. But before going to 3D, they went ahead with 2.5D. 2D, 2.5D, and then 3D. Right? 2.5D is wherein you have multi-chip model. Just think about all these chips, and they are connected through interconnects, right, in the same domain, or sometimes beneath that. So this is what the interposer we call it, right? This is 2.5D silicon which we are talking about, and this is where you keep on connecting. So it's not 3D, 2.5D, all kind of things people have explored, and working a lot in this. Believe me, electronics is one of the areas which is seeing so many changes. It's really very hard for anyone to sustain with all these growth. Really, you people are really wonderful. You talk to a computer guy, they have few algorithms that they work out with, private optimization, and all those kind of things. They're happy with their good job and all those things, but electronics engineers, they have to read out from diode, BJTs, MOSFET, FinFET, tunnel FET, so many FET, so many versions, right? And then interconnects top of that, morphing, all those things, memories, logics, everything happens. And it's all because of people like you, persons from computers and other areas are thriving. Okay? It is we people who are making all these changes. It's really hard to catch up with all these things. Good work that you all are doing. Still sustaining with electronics. Good. Now actually, this was something that we carried out, still we are carrying out with interconnects. We are using now machine learning and other efforts to find out how many repeaters would be required on those many things. But just as an overview, this is what we have done most of the time done up to 2015 or so, still continue but slowly. And then I started off in the area of spintronics. Now, there might be a question, why did I start with spintronics all of a sudden? What was going behind that? Is it that you had some dream when you started off with spintronics? No, it was not that. We, came across one of the research work where spin waves could be used for transferring the data. And spin was considered to be really good effect of transferring the information from one end to another. But we realized when we did all the analysis, what we realized that probably these spin would be good enough for only lower length. As the length increases for interconnect, they won't be really good because they have their own relaxation time, spin relaxation. They will be there for some time, spin, and then as they move on, they will lose their spin. And therefore, it was not good for global interconnects. And most of the research across the world was being done only for global interconnects. But then, during that time, we realized that yes, spintronics is really good for memories. Why don't we start seeing into memories using spintronics? One of my students actually, who started off from this area very good, she wrote we started off with this spintronics area at that point of time and realized that it's really good, started looking into memories and devices. So at that point of time, MTJ was something very new, magnetic tunnel junction. I think you would have heard about this word now. Ashwin was there, right? Yes. So did you had a talk about MTJs, magnetic tunnel junction?
Yes, sir.
Sure?
Yes.
Seems others are not convinced.
No.
Did you talk about magnetic tunnel junction?
Yes, sir.
Okay. So this magnetic tunnel junction at that point of time was very good. We, came up with different models for these MTJs and started doing, MRAMs. But then if you see over here, you have a silicon substrate and a transistor, right? An MTJ sitting over there. This MTJ is a storage element. So we work more on circuits aspect. We consider that people like Ashwin have created a good device, storage device, and now we can use it in circuit, right? That is what we do. And how can we explore it for different purposes? That is what we often do. So we created all these MTJs, models, and started using it. But if you can see, I think all of you are aware of SRAMs and DRAMs.
Yes.
Right. So how many transistors are required in SRAM? 6. Minimum 6. It can go up to 10. Right. And why do we go for 10 and 12?
To reduce power consumption.
Reduce power consumption. We are increasing the number of transistors. I think most of the time we try to look for more reliability issues. That is something which drives us to have more transistors. But anyway, and how many transistors does DRAM has?
One transistor.
Minimum one. It can have 2 transistor DRAM, 3 transistor DRAM, right? Again, reliabilities. Can you see here? You have 1 transistor and 1 MTJ. Can you compare a DRAM, 1 transistor DRAM with this kind of structure? In DRAM, you require 1 transistor, and what is the bigger element? Capacitor. And that capacitor, how big it is? Sometimes bigger than your transistor or almost equivalent, or maybe 50% of that transistor size. Did you do some kind of analysis of that, or looked into some of the figures actually in the presentation like this? Any inputs from your end about DRAM, especially the capacitor size? It's quite big in size, right? And that will be trenched into your silicon itself. It's not hanging somewhere around. Whereas if you see this was the convincing point. Industry is not ready to put on any money until they see, they do not see anything good, anything really good, very good. If I tell you that, I have a good car engine with me, please spend 20 lakhs on it, will you be ready to spend? No. I'll see it at least for 5 persons working on it and something, very wonderful, only then I am ready to spend 20 lakhs. Nothing before that. Don't come to me again. I keep on convincing, this is published, this is published, this is good, this is good. No, man. Unless this is not seen by me for at least 5 to 10%, I won't spend 20 lakhs. None of you. And similar is the case with industry. Now, this is something which convinces industry to go on with spintronics. Right? Now, what important you are seeing here in comparison to DRAM? Now, what I am trying to convince you people is, DRAM, we often switch from SRAM to DRAM for what reason? Size, density, right? Otherwise, DRAM is worse as far as speed is concerned. It can never match SRAM. When it comes to the core of a CPU, you will always go with SRAM. Your mobile phone cost will go very high because of SRAM. Because you are putting up more and more registers, more and more SRAM within the processor. And that is all SRAM, level 1 cache. The external memory card that you use as a cost can be GBs and sometimes in terabytes. The external memory that you use, mobile hard disk, how much does it cost? $5,000 for 2 terabytes. And a mobile phone, just have a comparison. The processor having 5 GB or 1 GB and the processor having 20 GB. The cost difference would be enormous. 1 GB phone you can buy it for 5,000 rupees. And for 20 GB you will be spending like 40 rupees. Although the processor is going to increase, but it's all cost of memory which is going to increase a lot. So DRAM, I don't care much. I'll be talking about memory hierarchy also. Different kind of memories that you use. Right? Now the question is, this figure that you're seeing convinced the entire gamut of industries that yes, we should go for spin-based memories or non-volatile memories. So all kind of memories that you talk about, resistive RAM, ferroelectric RAM, memristors, everything that you talk about, just think about which memory actually has been accepted by industry and is working. Just have a look onto it, right? By the time we come for the next lecture. Think about it. Which one has been accepted by the industry? Now, I'm just trying to make a comparison of DRAM and this one. Now, what important thing that you're seeing is, this size of transistor is fine. Is it that MTJ is taking the silicon area? No. Whereas in DRAM, capacitance is taking the silicon area. It is trenched into the silicon. Now, when you talk about MTJ, it is hanging over your transistor. It's 3D kind of structure. Nothing to do with your silicon area. Apart from this, what you see is the MTJ is of very small size. Very small size in comparison to your transistor. This is a planar transistor. So what this Shivam Verma actually thought of while going through this research, he originally thought of that, what we are seeing is still the overall area of a single cell is all because of this planar transistor. MTJ is still very small. So why don't we use a gate all around which is smaller than your planar transistor? Oh, I said wonderful idea. Why don't we go ahead with it? That's fine. Let us go ahead with this gate all around transistor. Still, what you are seeing is gate all around transistor is still occupying more area in comparison to your MTJ. MTJ is here, and gate all around transistor has much more control because it is GAA, gate all around. It has more control, more driving capability, right? So we could achieve same performance using gate all around transistor using this MTJ stack. And still transistor is bigger. MTJ is hanging over your transistor. So size wise it is lesser than DRAM. So you can increase the density by several times in comparison to your DRAM. Industry got convinced, yes, this is something wonderful. Right? When it comes to performance, it is far better than your DRAM. And do you know, in most of the server class memories, this is what Everspin has already, Everspin. Just write down Everspin. Have you heard about this company's name, Everspin? No. Do you have mobile phone with you? No?
Yes.
Just Google it. Everspin.
Everybody knows. Spell it.
EV. Magnetic lamp. Can you see Everspin?
Yes.
So this is the company which is leading a lot in spin-based memories. Everspin. It's already listed in New York Stock Exchange. It has already manufactured a lot of spin-based memory, and this is the company which claims that they have replaced entire DRAM in server class memories with MRAMs. DRAM was actually started off in 1970s, and in 2020 they actually celebrated 50 years of DRAM being there in the market. Intel, longest duration of one device which kept on going. So you had DDR, many other kind of memories which were there. Now that has been phased out completely by MRAMs, as claimed by Everspin. So it's all happening. It's not that we are just talking about research. It's something which is going simultaneously, and the entire spintronics industry has exploded like anything. So fast. And do you know when the entire game started up? 1970s, there were two researchers, Albert Furt and Peter Grunberg, who noticed a phenomenon that in a magnetic field, if you place some kind of material which is ferromagnetic material, its resistance will change. This is a simple thing that we observe. The resistance of ferromagnetic or a magnetic material will change as you change the magnetic field. And both of them conducted these experiments separately. It's not that Albert Furt and Peter Grunberg were working together. One was in France and the other person was in Germany. So this was done in the 70s, but then the industry went on very slowly and steadily. Researchers are 20 years ahead, this is what I say, at least 20 to 30 years ahead of what industry accepts. And they were awarded with Nobel Prize in 2007 or 8. You can just confirm. Albert Furt is still alive. Peter Grunberg is new. Albert Furt, you people can just Google it out, Albert Furt. I'm just giving you some keywords, right? 1.5 hours is not good enough to discuss about spintronics, right? It would take several months to understand what actually spintronics has been doing, right? So just look into these Albert Furt. Just find out Albert Furt and Peter Grunberg. Both of them actually started off with this research area, awarded with Nobel Prize in 2008 or so. Right? There are a lot of institutes named after Furt. There are some of his students are from China. by Silchar, who started off with FERT Institute of Microelectronics. That is what, that is how he has been so popular. So, with this spintronics coming up, all these kind of MTJs were also introduced later on. But let us, look into some of the other aspects that spintronics actually has bombarded. So if you see spintronics, the areas where we have been working now as of now. So memories is primarily which started out the spintronics area to boom, right? And then people looked into different other kind of devices also. So MTJ is the primary device which started out, and then we'll be briefly discussing about it as well. Then you have domain wall which started off, and as on date, a lot of work is being done on SERB. SERB based on ferromagnetic material, anti-ferromagnetic material, ferrimagnetic materials, all kind of magnetic materials which are explored. So this is what the device's end is concerned. When you go to memories, you have single level cell memory, you have multi-level cells of all these kind of memory, and then of course a lot of computing in memory kind of stuff that can be done using these spin devices, which can be really fantastic as far as the performance is concerned. The spintronics area, because you do use only magnetic materials, and they are not very much affected by the electron charges, and inherently they are very much radiation hardened also. So that way radiation hardening can be taken care of over here. Apart from this, the spin devices, they do demonstrate different kind of functionalities, and that way it can be really useful for your AI neuromorphic kind of computing also, where we have been looking into non-spiking and spiking neural networks also. And I think one of the areas which is really booming up very fast is your quantum computing. Right? And within this quantum computing area, I think if you can just look into further details if you are interested. This area itself is a completely different world to work on. You have different kind of gates, Toffoli, Fredkin, and all those kind of gates, very complicated. But everything works on a qubit, right? And these qubits can be very well made out using, spin-based materials. So spin qubit is something which we also worked out and tried to realize all those kind of quantum structures, which can be used for computing. Not only different gates, but also we went on with Fourier transform, up to Fourier transform, adders, all those kind of logics, and then up to Fourier transform. And of course, you do have a lot of things that can be done using these kind of devices for logics, and within that you can have full adders, compressors, multipliers that we have realized. But in a nutshell, what I understand is spintronics would be doing really well in memories. That is where it is making very long strides and very strong strides. Reason being that different companies have started out with these kind of memories and already placed into your laptops and computers and mobile phones. Replaced completely NAND flash and replaced completely your DRAMs also. So that is what is being done over here. So these are some of the areas, including hardware security, because if someone is working on hardware security, then you will realize that if you have more and more variability, it is good for security reasons, right? So that way, MTJs can be made out in such a way they can have more and more variabilities also. And all these spin-based structures or magnetic materials are often affected by your thermal variations. That is one of the biggest issues within spin devices, and that can be harnessed very well for your security reasons, for making all those hardware secure, puffs and all those kind of things. Right? So we are working on this area too. So these are some of the areas where we have been focusing a lot. And if you see the total, the talk would be, I don't know how much we'll be able to cover, but this is what the outline is. Even if we cover up to SOT, that would be good enough, as far as my understanding goes. So let us see how things have changed with time, as far as the memories are concerned. So it has gone through a long journey, and if you see last, maybe 4 or 5 decades, you can see that the changes have been rapid. If you see, one of the areas which have been changing, a lot, which has been facing all these changes a lot, is memories. How many of you have seen these music tapes? I think all of you would have seen, where it was all based on magnetic materials, right? You used to play it on the one side, so on the other side, other set of songs. So the cassette used to have 10 or 20 songs, something like that. And the size and the reliability was so low. I can never forget that whenever I had to go for a talk, I used to carry at least 3 or 4 floppy disks. I don't know, which one is going to work out well. And other than that, still I used to print certain transparencies also. If nothing works there, at least I should have my transparencies, which I can use with overhead projector. So that was the state of affairs with memories, maybe 20 years back. Then came your CDs. So magnetic materials were discarded because of reliability issues. I think those who have heard to those cassettes, I think they can realize that if you put those cassettes in some harsh sunlight, everything used to vanish. Or maybe if you used to listen to those songs number of times, went something wrong, right? And that was the reliability issue that we used to have these kind of memories. Then CDs still did well. The capacity of these CDs went up really very high. So movies, I can understand that even these cassettes used to have all these kind of memories, which could display all those videos and frames. So the capacity was too high there. But CDs, although being brittle, right, but you could store a lot of memories over there also. And DVDs, again you saw a change. I think you all have witnessed so many changes, and changes are still going on. You can talk to your friends, oh man, so we have seen so many changes over our life. Every decade, the technology changes. And as on date, I'm quite comfortable to carry my, pen drive with me, having a capacity of so much of GB with me, right? And imagine 20 years back or 10 years back, I can realize during my master's also, it was so terrible to give a presentation. The biggest worry was that whether the disk is going to work or not. I'm not bothered now. I don't have to carry anything. More reliable designs, so on and so forth. And all these 1970s when Peter Grunberg and Edward Furr came up with these magnetic materials. So all this duration of time, until now we had been not discussing about spintronics a lot. But last 50 years, it's all reliability that was being worked on. All those reliability issues were being addressed. And now since it is highly reliable, Everspins have come up with replacing all these DRAMs by spin-based memories. They've already done, and believe me, they are still working with. I have to go back. They are still working with MTGs, simple MTGs, not even spin orbit torque, which is another class of memory which is much reliable. They are still working with only MTGs. The good thing is that the CEO of Everspin is an Indian guy, and happens to be from Haryana itself, my own state. So that makes it all good. So things have been changing a lot, and if you see semiconductor memories have been seeing a lot of changes, and in fact a lot of applications everywhere. You see that all these kind of memories have been making a lot of strides. And if you see all together, I think if you look into all these kind of different type of memories also, you have different hierarchies. Either it has to be used in your embedded system, or it has to be used in a standalone system, So you need to have either your NVS RAM, storage and accelerator, where you have to have some kind of memories which are really fast. Then persistence memories for servers. Then you have core or data storages in form of eFlash in different MCUs. Then memories in form of your EDRAM or SRAM and your CMOS image sensors. You find a lot of applications in different areas. And then when it comes to CPU, you need to have highly reliable and highly fast kind of memories. I don't say that Spintronics based memories have replaced SRAMs. Still, SRAM is something which is fastest. But if you have some kind of spacing between DRAM and SRAM, spin-based memories are taking up that space very quickly. Right? And with different research being conducted, wherein MTJ, as of now, MTJs were earlier switched by magnetic fields on externally applied magnetic fields. Later on, we used to have this electric current that was used creep into your VLSI chip. And now people are looking about optically switching all these pin-based devices, MTGs. And once it is able to realize, probably they would be competing very well with SRAMs also. So industry is looking into all those kind of aspects. And when you see into memory market, it's really growing very fast at unprecedented rate. And if you see your market by time, if you see MRAM is making its own, area of applications and areas also increasing a lot, taking up most of the area for DRAMs. So DRAMs still is there, flash RAMs, SRAMs, this is where others are here, MRAMs. Quite an important kind of areas to work on with. And keeping all these things important, right? Memories, everywhere memories, right? So we started off with one of the journals with LCS also, wherein I'm looking after the affairs of this journal, which is all targeted, for materials, devices, circuits, and systems based on these memories. You can just look into some of its very new journal which we started off and published with few papers right now. But of course, you can look into those prospects which are there with memories. Okay? And in case you plan to work on memories, welcome to some of the good articles. So we have really good articles from across the world who are working either at your materials level or at circuit level or at your system level. They're all working with these kind of memories. And you know that all these kind of memories, I don't think so that we have to talk much about it, but these things are already there, non-volatile memories for a long time. Mass production for them has been already there. Some of the emerging ones are your MRAM, which has already made out roots into semiconductor industry. Then you have ferritic RAM, RERAMs, PC RAMs, and if you talk about, there was one talk which I was just attending to where a person said that you name the alphabet and based on that you'll have a RAM. OXRAM, MRAM, CRAM, everything you name the alphabet, you will find some kind of memory based on that. So memories is seeing so many changes as of now. Okay, so I think we can stop at this point of time and have some questions before we go ahead with some SRAM, DRAM basic structures, and then we'll jump into spin kind of memories. So this lays down a good foundation to understand why memories have gained so much of importance and what kind of memories are really emerging and what kind of memories have already made a strong inroads into the semiconductor industry, what kind of memories have already come up with production and how many of them have been used also in your systems as well. So we'll have a next part of talk also. At that point of time we'll be looking more into spin-based memories. Any questions that you have? Please feel free to ask anything, right? Nothing only related to memories, but of course anything unrelated to memories or unrelated to spintronics also.
Sir, MRAM doesn't interact with Earth's magnetic field. is it affected by?
So when you talk about earth magnetic field, people are even more concerned about one MRAM affecting the another MRAM, right? So this would have been really true in case we would have been switching that MRAM using magnetic field only, right? So we are no more switching those MRAMs using some external magnetic field. We are using only the current generated magnetic field, which is going to switch over these devices, right? So we often ensure that these MRAMs are placed with some distance with each other so that they do not get switched, right? That is what we see. And if you see furthermore, very good question that was. Apart from this, when you see, we talk about multi-layer MRAMs also, right? So here we have a heavy metal which generates magnetic field because of spins, and these two layers which are free layers, this one and this one, both of them would be switched in opposite directions. So they are coming so close, still they are coming so close to each other, and they would be switched in different directions. So magnetic field generated by Earth, no worries.
Sir, electromagnetic interference is there, na sir. We are having the devices inside the circuits. So in general, we are having electromagnetic interference.
Right.
So like for example, if we are using the television, so we are switch on the mixie, so we are having some disturbance. So in the like that, if AFRAM so faces that such type of interference.
So if I go back, right, if I go back to general perspectives, electromagnetic interferences do affect your even general chips that you have. Leave aside MRAMs. They do affect these kind of chips. But then we have to ensure, we have to keep encapsulate all these kind of chips in such a packaging so that it doesn't get affected by others, right? Other magnetic fields. That is what we ensure. And even still, if you have some kind of electromagnetic interferences, maybe in space, right, or maybe in nuclear reactors, right. So there is a completely different domain of research that goes on, and completely different kind of packagings and designs that goes on, which is called as radiation hardened designs. So there, all these kind of things are taken care of very well. Right? So if you are using it for domestic purpose, they'll ensure that whatever designs you make, electromagnetic interference, whatever is there in that atmosphere is taken care of. And if you have to take the same device to some nuclear reactor or some space station, it won't work very well. You'll have reliability issues over there. But then the design and the fabrication is aligned accordingly. So that is something which reliability issues have to be taken care of. And it does affect, and the designs are accordingly tuned. Good question. Yeah, feel free to put up questions.
Is this because we have this in the garden?
Yes, can you repeat?
Is that the reason we have in the garden?
Yeah, of course. Encapsulation is itself a big area of research and work, where the fabrication engineers have to do it. So they do, not only test for electromagnetic interference, but mechanical strength also. So there are many things that they have to look at. Is there any further questions? Yes, please.
When you design the gate-all-around transistor along with the membrane,
Yeah.
so what was the dimension of that gate-all-around transistor?
So-
and can we go? And the second part of the question: can we go 3D with that device? Is it possible?
Yeah, so it's a really good, right? And what would be, how the fabrication of these kind of 3D transistors can be done, right? So I think for this I have to quickly go to those slides which are there, maybe I'm not sure. It would be nice, yeah. So that current is something which is important for us. And that current, if we are able to, get it through planar transistor or through a gate-all-around transistor, that current should be equivalent.
Yes.
And what we realized that the size was reduced by 1/3 overall size. So previously it was something like, for example, Landis Corporation came up with a size of say 6 f square, and f is your feature space, and your GAA with GA we could reduce it to 4 f square. So 1/3 reduction, 33% reduction in the overall size, with the same performance, same driving curve, without any issues of performance, right? So this was more specific for the area. Now the other part of question is, can we realize 3D circuits or 3D designs? Yes, we can do it. The only thing is that you have to run a metal layer below the substrate also.
That will be the baseline for the bottom layer.
Because you need to run all those source extensions below this cross. This was one of the important questions which we had to handle with the reviewer for this paper. Any more questions? Yeah, feel free to put up any question. As I said, nothing related to only this.
So
Anything.
over here we are using like 2 devices. One is FET and the second one is MTG.
Yeah.
MTG. So instead of that, if because FET is already we are using over here, we can use FET
You
for
mean to
memory
say,
applications.
you mean to say, good question again.
Because dimensions remains almost same. Just
You mean to say, if effect, right?
yes, sir.
But then, in that case also we are going to use some, kind of different material, right? It is not ferromagnet, it is ferroelectric.
Ferroelectric.
So
Yes.
ferromagnet and ferroelectric are two different kind of materials. So ferroelectric FET is still, under investigation. It's not still, commercially it's not still available in your systems.
Yes.
And these silicon-based devices are already there. So industry would be, much more comfortable to use these kind of devices which are already established, instead of coming up with other research areas. Probably your question would have been much more appropriate had you been asking about why don't we use a spin FET, right? So there is spin FET also, which some of the groups started working on with, and still looking into those areas, but not released yet because of other pertinent issues. But anyway, it's a good question. Anything else? Yeah, please. Go.
So I will move like general question.
Yeah.
Like we have seen a lot of this MRAM, and yesterday we have got a lot of motivation about PC RAM.
Yeah.
What about this RRAM? Does it have any prospects in the future?
Yeah, of course. So Professor Jawar Singh, there are many, in fact, Shritosh also would have spoken about molecular RRAM.
But what about this oxide based or like
Yeah,
filament
oxide based, it took off, but did not go to the industry. The pertinent reason, in nutshell, what I can speak about is the reliability. Right? So reliability is something which is very important for any design. If something goes wrong in a chip, some device, the entire chip is not going to work, and that is where the entire, losses have to be taken care of. So that way, reliability is something which is very important for any device, and oxides are not that reliable. And that is why, Shritosh would have talked more about molecular. But MTJs are now much reliable. 50 years have been already spent on it. It's nothing new. MTJs have not only been used for memories, but before coming up with memories, the read head, if you see the hard disk drive that you were using earlier it was magnetic materials, then it was laser assisted reading that was done. I think if you would have opened some of your hard disk drives, it used to have a laser source also. And then it went on with MTJ read head. The sensor head was replaced by MTJ. Stuart Parks. Stuart actually came up with that MTJ read head. and that MTJ based read head would increase the storage density of your hard disk drive by 500 times. I'm just claiming, 1/3 improvement. And this person with MTJ read head could increase the storage density of your hard disk drive by 500 times. It was a huge change. Stuart is still alive, right? And he was the first person to come up with real application of MTJ long time back. So MTJ or sprint-based memories is nothing new. It's already there for a long time. Only thing is that real applications and the industry have already geared up with replacing all these DRAMs by MRAMs, maybe 5 years or 6 years back. So Oxram was your question, right? Not that RAM. And that is why all IRAMs have been having so many kind of versions. People have tried out all kind of versions for that. Yeah, anything further? If nothing, very nice interaction with you all. I think we'll be having even more interaction after the lunch. Thank you.
Thank you, sir.
So we'll have our next session by Professor Zabar Singh from IT Patna. Our next session will begin at 11:15.